So the idea of ANOVA is that it's going to compare all of our groups together at once, and hopefully what that's going to show us is whether or not there's any difference anywhere at all. So let's now switch over and start playing around with our ANOVA because it makes more sense when you actually see it. So we're now using the soy dataset. Now, something that we didn't do before was look at our descriptives, our univariates and our bivariates. But unlike regression, with ANOVA, we test all of our assumptions when we're looking at the descriptives. And this is more so the case because we can actually do it at this stage, whereas with regression, you actually need to run the regression to get the residuals. And because all the assumptions are interested in how the dependent variable behaves at each level of the IV, we're actually going to be looking at bivariates more so than univariates. Especially if, for example, you're expecting your dependent variable to have different scores across the levels of your IV, you're much more likely to see a multimodal distribution because you're expecting different means. So it doesn't always make sense to look at univariates, but you can do it anyway. We're going to focus on bivariates. Now, because we are interested in the DV across different levels of the IV, we're going to use a command called tabstat, which is designed specifically for this. We are still going to look for all the normal markers of normality. We can look at Shapiro-Wilk, but we're not going to today. Okay, so we've already spoken about this dataset, soy.dta, and we said our dependent variable is called sp_count, so sperm count, and then smeal is soy meal, that's our categorical IV. So the tabstat command, it is tabstat dv by categorical IV in brackets, and then we're going to have the different stats that we want. In this case, the n, the mean, standard deviation, skew, kurtosis. Ooh, we have an error. So the error here was that I didn't have a comma before my commands. And now it works. So what we can see here is the different labels for our categorical IV, and then in here is all the data for sperm count. And what we can see is we have the no soy meals have a mean of 4.98, 1 soy is 4.61, 4 soy 4.11, 7 soy 1.65. Same means we saw before. So restructuring the dataset doesn't change the means. If we look at our standard deviations, something we notice is that 7 soy meals has much, much smaller standard deviations than the rest of the sample. And so this could suggest that actually we violated the assumption of equal variance. If we look at skew, we can see that our skew statistics are all above 1, all above 0, particularly for 4 soy meals. And our kurtosis is all over the place. Really, 7 soy meals is the most normally distributed out of all of them. But even then, it doesn't look too crash hot. So let's go and look at our histograms and just see how problematic this is. So now when I'm running my histograms, I'm using by smeal to actually produce 4 histograms at once. And it looks absolutely horrendous. There is nothing that even suggests normality. We have huge positive skews in all cases. So despite that, let's go and test equal variance. So we're doing this by using the robvar command. This is going to run our Levine's test for us. And it's robvar dv, comma, by categorical IV. Now it produces our means and standard deviations again for us, which is great. I would have used this before, but I also wanted my skew and kurtosis. Now there are 3 different kinds of equal variance, W0, W50, W10. W0 is using the mean, W50 uses a median, and W10 uses what we call a trimmed mean, which basically takes the 5% most extreme scores off either side of the distribution. So you're effectively losing 10% of the distribution. We're going to look at W0 in this course, so you can ignore the other 2. And what we see is W0 is significant. Now, the Levine's test's null hypothesis is that the standard deviations across your groups are equal. So it's just like Shapiro-Wilk, where we say your distribution, the null hypothesis is that your distribution looks like a normal distribution. The null hypothesis of Levine's test is that you've met the assumption of equal variance. So the fact that we have a significant p-value here tells me that we don't. We haven't met the assumption of equal variance. Our p-value is less than 0.05. We have violated the assumption of equal variance. Our standard deviations are significantly different from each other. Now we have a balanced design, so these aren't major issues. But in the last tutorial, we'll come back to this data set and we'll consider an alternative approach, an analysis that actually gets around this. But for now, we are going to blindly proceed forward and analyze the data as if it was perfectly fine. So now that we've looked at the distribution, we've looked at the means, the standard deviation, skewness, kurtosis, we can now move in and actually fit our ANOVA model.